Hello everyone. In this video we will continue to examine topic 9.5, the Doppler effect, and in particular we will continue to examine moving sources. Okay, in the last video we examined the relationship between the emitted frequency and the detected frequency or observed frequency for a moving source moving towards a stationary observer. But this same situation gives rise to the following question. What does the analysis look like for a moving source, moving away from an observer? So what would happen if the observer were over on the other side? We can again use the simulation to get a general sense of what's going on. So instead of a source moving towards the observer, now we can see that our little person is detecting sort of longer wavelengths. And we're going to try to use the same analysis to figure out what that detected frequency should be. All right. So how does the observed frequency f prime depend on the velocity of the source and the emitted frequency? Same question as last time, except now we're going to focus in on an observer at A rather than an observer at B. So instead of the source moving towards the observer, the source is now moving away from it. Okay? The thing to recognize is that just as before, the source emitted its initial wavefronts. They're reaching A and B at the same time. And we wait one period later, and now the source is at S prime and emits its next wavefront. So the thing to recognize is that the detective wavelength for an observer located at A, right, the detected wavelength in between the two wavefronts will be longer than it was before rather than shorter. So instead of being compressed, it will be extended. And by how much? By the amount that observer has traveled in the meantime. So now, by the amount the source has traveled in the meantime. So the source is now over here, and the source emits its second wavefront right at S prime. So the detected wavelength by the observer is lambda prime. And notice that lambda prime is longer than the original wavelength v over f. So we run the same calculation, and we find that indeed they have a longer observed wavelength prime. So lambda prime is v over f, that's the original wavelength, plus the source velocity divided by f. Notice that this term right here, right, that's the same as the velocity of the source times the time period, which is, for me at least, an easier way of understanding why that is a distance. So that right there is the extra distance traveled by the source, and so lambda prime is then equal to v plus us divided by f. In comparing to the previous calculation, we notice that all that has changed in the calculation is a minus sign. So we then do the same steps to find our observed frequency here. We take the observed frequency is equal to the wave velocity divided by the observed wavelength. And we get that that is equal to Vf divided by V plus U sub S, plugging this formula in and inverting it. And therefore, f prime is equal to v over v plus u sub s times f. Notice that the effect on the frequency, if the source velocity is bigger here, is to decrease that frequency, as you would expect. The note gets lower, okay, lower in pitch, if the source is moving away from you faster. So as expected, this equation makes sense, and we can summarize these equations like so. So the detected frequency f prime is equal to v divided by v plus or minus u sub s times f. And that plus or minus is plus is away and minus is towards. However, I strongly recommend that you not try to memorize which is plus or minus. I think that is a fool's errand for reasons we will see later. Instead, know that the formula is in your data booklet, and know that you can always look or think about whether it should be higher pitch or lower pitch. So my recommendation for the problems using the Doppler effect equation is to consider the physical situation, consider whether that pitch will be higher or lower, and then pick the minus sign based on that. As we'll see, there'll be other formulas, and the positive minus, positive negatives get a little bit confusing. So my strong recommendation is simply use the formula as given and pick the positive or minus sign based on whether you expect that frequency to increase or decrease.